So, once again, what we want to do is kind of go over, I'm going to go over the big picture overview right here, right? And we're going to look at, because we're going to be looking at a couple of things that you can take this picture, the slide that you have on the end, take some notes right there, the questions that you're going to answer today. And so this first one here, right, there's oxygen. This is yesterday, everything we talked about was getting air, right? This bulk air movement. Right? You're doing the whole pressure, volume differences by expanding your lungs, bringing in air, right? And then there was things that were maybe stopping that, conditions or something, right? So, but everything there was just getting that air right down there through bulk flow, pressure differences from a high to low pressure, creating those pressure differences with your chest movements. So now we got the oxygen, got it in that little air sac, right? And so from here, right, we want to ask ourselves, how does oxygen, right? It's going to diffuse from the air media, right, across cell membranes, two cell membranes, the lining of the alveoli right there, and then it's going to go through the lining of the capillary, right? And in between there's going to be a little interstitial fluid. Right, so we want to know about how it gets from one place to another, right? So one of these things is we're getting into is like air, so really oxygen moving, let's say how. What are the factors that mediate oxygen moving from airspace to plasma over there? And here, we'll get into things from way back on lecture 1 or something about diffusion, or lecture 2, whenever we did that stuff, right? Diffusion, right? All those diffusion properties. What are some of the diffusion properties? Anybody remember anything about diffusion? Right? All these properties that allow for the rate of diffusion, right? Because we want to maximize, right, how we get oxygen into the bloodstream.
Smaller surface area.
And it's small, big surface area. We'll write these as we get along here, but surface area, factors of surface area, the distance that it's got to travel from one side to the other, solubility, right, the permeability of that, all those are directly proportional, right? The distance it's got to travel is actually inversely proportional, right, as we'll see. Right? But it's got to go from one side to another, right? And it's going to go from an area of higher pressure to lower pressure. Right? Again, but in this case, it's going to be that so-called partial pressure of the gas, right? I mean, it's a concentration gradient, that's what it is. We'll refer to these concentration gradients as partial pressures, right? So it's going to move into the bloodstream right here, into the plasma right here, but oxygen is not very soluble, right? In fact, it's very little soluble, right? You're going to get in there and it's got to go immediately, it's going to be soaked up, right? It's going to enter the red blood cell, and then it's going to enter the hemoglobin, right? So, number 1, right, here we get into this whole, all this is like one half of the lecture right there. How do we get gas from one side to the other, right? Based on pressure differences and all the properties of diffusion. And then the second part, we're going to be looking at the transport of oxygen and carbon dioxide, right? And what about the properties of hemoglobin, right? Well, properties of solubility. How does hemoglobin, right, transport oxygen? And number 1, how does it know to pick it up right there? Right? How does it know to soak up every little last bit of oxygen right there? Which doesn't seem like a hard question, right, until you get to the fact that it's going to get to the tissues and then drop that oxygen off. Right? So basically, we're asking, how does hemoglobin transport oxygen? How does it know? And of course, that's like not really a thing. It doesn't know. It just acts by mechanical properties. How does it know when to pick up and drop off? Because it's going to do that in a very seemingly intelligent way, right? It's going to pick up where there's a lot of oxygen in the near the alveoli. It's going to take it all in, like most of the oxygen, because gases, again, the oxygen doesn't really it's not soluble in the plasma. So it's all gonna be transported through hemoglobin in red blood cells. And then over here, when you get to this tissue over here, right, it's gonna drop it off. It's gonna say, you guys need the oxygen. I'm gonna let you off right there, right? Because these cells over here, they need the oxygen. They're gonna use it for cellular respiration, right? That's the whole purpose of oxygen, to make ATP right there. And if you're a not very active cell, right, maybe you don't need so much oxygen. If you're a very active cell, you need a lot of oxygen, and the hemoglobin is gonna drop off a lot of oxygen, as much as you need, as much as that cell needs right there. And so it's gonna know somehow how to, how much to pick up, how much to drop off, right? So it's pretty amazing, right? And then, second question is, if these are really hard-working cells, what are they producing? Waste, right? Carbon dioxide, waste, right? All sorts of things, right? Maybe excess hydrogen ions, because it's a hard-working muscle that went into anaerobic metabolism, right? So there'll be a whole bunch of signs that this cell is really working hard right here. One of them is, the most obvious, is a lot of CO2 production, right? So in that case, CO2 is gonna be produced. It's gonna be produced in mass amounts right there, and it's gonna diffuse from this area of higher concentration to an area of lower concentration here, okay? This is just all big picture stuff, right? We're gonna go over all this stuff right here. So, the second question is, how is CO2 transported? And what are some of the important things about CO2 transportation in the blood? Right, it's going to diffuse through. It's got a little bit of more solubility than oxygen, right? But we're going to see it's actually carried in part by hemoglobin, and in part it's going to be made by the action of an enzyme into this bicarb ion, a bicarbonate ion. That's going to be transported through the blood, through the plasma, right? And that bicarbonate ion is your most important extracellular buffer in the body, right? That's gonna help maintain pH, so it's a very important part of that, right? So how is CO2 transported? So these are big questions, right? And then it's gonna be transported all the way back. It's gonna go into the right atrium, right ventricle. The pulmonary artery is gonna pump it into the lungs, and that CO2 heavy blood, right, is going to diffuse from a high area of higher concentration, partial pressure, into the airspace, into a lower concentration, right? So that's basically all we're going to cover today, right? Which seems like we're already done, but we're going to go into a little more detail about that, right? But this is the big picture you want to be focused on here, right? So the reason, the whole purpose, of course, of oxygen, this is the main purpose of getting oxygen to the oxygen-starved tissue and getting rid of CO2 and leaving proper amounts of CO2 in your body, right? So when you have too little oxygen, right, that's the condition of hypoxia, hypo, under, oxia, meaning oxygen of some sort. Hypoxia, and so that's what the body is trying to avoid, low oxygen conditions. There'll be definite physical signs when you have under oxygen right there, that are pretty apparent right there, right? But there's going to be detectors all around your body that are searching for signs of low oxygen, and they're going to tell your whole homeostatic reflex centers to make amends, like try to do something to respond to that, right? All these homeostatic mechanisms, right? Same thing, carbon dioxide. In fact, more so, there's carbon dioxide, too much carbon dioxide floating around. There's little so-called chemoreceptors, right, that pick up carbon dioxide, and again, they're going to tell the brain somewhere to do something about that, right? Or local tissue. So those are your two big indicators, right? The levels of oxygen, too low, carbon dioxide, too high, right? That we're going to take action right there. And the body's going to take some kind of action. The other thing, which we won't be discussing today, is pH. Right? That's one of the other things, a kind of indicator that there's something wrong in your respiratory system and you need to deal with it in some way. And the respiratory system is going to deal with it. So these are things that the variables, oxygen, carbon dioxide, and pH, these are the three variables that are constantly monitored and maintained and responded to, right? So the second part, again, breathing. breathing, ventilation, you're just bringing air right, down into the alveoli, right? And here we're gonna start talking about gas exchange diffusion properties, right? It's gonna diffuse across the membrane of the alveoli and the membrane of the capillaries to get into the blood, right? And it's all gonna happen, again, as always, constant theme here, concentration gradients, partial pressures, right? The partial pressure of a gas. Your gas exerts a certain amount of pressure. Each element in it is gonna exert their own amount of pressure. And so you'll see in the alveoli, you're always gonna see these numbers, right? 100 millimeters per mercury. The carbon dioxide is gonna be something like 40 millimeters per mercury. And then that is what's gonna be the concentration in the pulmonary veins, right? Heading back to the heart right there. Right? That's gonna be the pressure and through the arterial system until they start delivering that. Right? So all throughout here, you can see the same kind of pressure because it's going from 100 to what it meets in the arteries over here as 40 millimeters, right? So you can go from 100 to 40, that's gonna be a big concentration gradient. That's the direction it's gonna go. Okay? So it's gonna travel out throughout there. Here, this 100 millimeters per mercury, this pressure differences is gonna be met with a 40 millimeter per mercury, right? 40 pressure, let's just say pressure gradient over here, lower pressure gradient because the cells have used up oxygen, so all the oxygen is gonna diffuse into the cells, right? This is all based on pressure differences. That is, when we're talking about gas exchange, the pressure in the alveoli has got to be greater than the pressure in the blood for that movement to occur. And the pressure in the blood of CO2 has got to be more than the pressure over here for CO2 to move back into that airspace, right? And the opposite will be true when we get to the gas exchange of the tissues. All that makes sense, right? I could ask any question like that. We're talking about pressure differences over here, right? This is what we want. This is like one of your main factors. And all these individual gases are going to do individual partial pressures, right? Right? That makes sense? All right. So all this is about how much oxygen you're getting in your blood, right? So all this whole lecture today is about how much oxygen, and well, also carbon dioxide, but the oxygen content, first part of this is all about oxygen content in your blood. And this first part about it, we're going to say, how do you get oxygen from the alveoli dissolved into the plasma, right? And then once it's in the plasma, what happens to it, right? And these are all the properties is influenced by, so when you look at these charts, right? How much oxygen is dissolved in the blood right here, and then is influenced by, right, the composition of air, right? And alveolar ventilation, what determines alveolar ventilation, right? The rate and the depth of breathing, your resistance, your lung compliance. These are kind of things we talked more about yesterday, right? And then today, in purple, right, oxygen diffusion between alveolar blood is going to be controlled by these factors right here, right? These diffusion factors. And then next, we'll go into the other parts, right? So here are the factors. Right? All these are what we'll be talking about mostly in diffusion, but the factors affecting gas exchange in the alveoli. So oxygen, reach down, and it's going to get, at this point right here, we're talking about what are the factors, right, that are going to create a high pressure, a lot of alveoli, enough so that it's going to diffuse from that high to a low pressure right here. And these are going to be, we want to maintain that pressure gradient is the first thing. Right? This is what we're going to talk about. Next we'll talk about diffusion rates. We won't really be talking about the blood flow through the alveoli right there. That's another factor, right? So first one is normal conditions, right? Most of those are pretty stable, but what could be something that you could experience if you happen to be climbing a high mountain right there is the fact that as you get higher and higher and higher, right, your total air pressure is less, right? It's kind of like anybody here dive or anything like that, or have you ever gone underwater below like 10 feet? You start to feel a lot of pressure, right? And that's because you got a column of water. The more water you got on top of you, right, the higher the pressure. Same thing over here. You know, air is basically sitting on the Earth's surface because of gravity right there. As you move up, there's just less and less of it as you get up there, right? So the total air amount, even though the oxygen is still 21%, right, it's much thinner. This is why they call thin air, right? So you get up there and you're breathing in normal, you're breathing in this much oxygen, then you're breathing the same rate and you're getting a lot less oxygen as you get up there, right? So now you have to, what do you have to do to counteract that? You have to breathe harder, you have to breathe heavier, right? Once you get into the, right? So that's gonna decrease, that's one thing. That's gonna decrease your pressure of the individual alveoli, the individual oxygen in your alveoli right there. Right? So altitude is one of your main, like, non-sort of pathological conditions, right? But most of the other ones are gonna be considered like pathological type of stuff, right? The other one, getting oxygen in your lungs, right? Alveolar ventilation, right? There's a lot of what we talked about yesterday. In fact, we have these obstructive diseases, excess mucus production, bronchoconstriction, right? Anything that's blocking the airway from getting the alveoli down, right? So enough air is getting in, there's not enough oxygen in there. Right? The other thing is when you have those restricted diseases, right? You're not breathing, you're having trouble breathing, you're having enough trouble with oxygen getting down there. Those are all the kind of things we talked about yesterday. All applies to the fact that you're not getting enough oxygen in the alveoli, your partial pressure is too low, right? There's not enough of a concentration gradient, and not enough oxygen is getting into your plasma right there. Okay. And then the other part we won't really talk about is, things that your central nervous system is constantly monitoring stuff. So for some reason, your CNS is, some of those parts are going to be blocked for some way. And I talked about my friend I saw lying on the ground, passed out with the blue lips. He was, basically what happened was the normal things that are responding to high CO2 levels, right, and low oxygen, they just weren't working, right? So with the fentanyl, basically what happened was whatever that drug is doing to make him feel like he's just climbed back in his mom's womb, made him also forget to stop breathing for some reason, right? All those pathways were kind of blocked, right? Those normal pathways that would normally detect these kind of things, right? So drug overdoses is often, one of the common things, especially with those opioid type of things. Okay? So now those are the things that affect, right, the concentration gradient in the alveoli. And there wasn't enough pressure differences, so there was the high to low part of it was just like a medium to medium, or even maybe low to high or something, so it wasn't moving across, right? And so once you do have enough oxygen in there, right, it's still got to diffuse across two membranes, right, through a interstitial space and into the plasma right here, right? So there's going to be a couple factors here all about this diffusion properties. And for the most part, what's always, if you're in a healthy state, rather, your surface area of your lungs, remember, hundreds of millions of alveoli, we're increasing the surface area of your gas exchange to something like, a racquetball court, right? So there's a lot of surface area, and if everything's healthy and working right, that's gonna stay the same. The permeability, which I'll talk about in a second, right? Basically, your two cells over here in the interstitial space is going to be relatively the same, right? Unless something's going wrong. And the distance in between here and here is going to be pretty constant. So all those are constant unless something goes wrong in a healthy person. And then the other thing is, of course, the primary factor over there is that gas exchange. Is there enough gas? Is the pressure gradient big enough for things to move across right there? Okay, so the diffusion, again, we have over here, we have alveolar oxygen space over here. We got oxygen in here, and we need to go through this, right? There's that aqueous layer with the surfactant in it right there. It's got to go through this aqueous layer over here, and then it's got to diffuse through the cell membrane, the apical surface of the alveolar cell, then it's got to diffuse across here, and then it's got to diffuse out the other side, right? The basal side of the alveolar cell. Right? That's a simple squamous. Remember the really, really flat epithelial cell. So minimal distance in between these two membranes. And then it's going to cross a very short interstitial space. Normally, right, you got a basement membrane, you got connective tissue, areolar tissue. Here you actually got fused membrane in between the endothelial cells, which are also simple squamous. And so there's a fused membrane, so there's minimal, basically, interstitial space in here, right? And then it's gonna go through this membrane over here of the endothelial cell, and it's gonna travel through here, and then it's gonna travel through here, right? Once you're in here, it's gotta go in here into the red blood cell. Right, but basically this distance over here is basically minimal when everything's working right, okay? When are things not working right is the question right there. Well, I'm gonna answer it. One of them, I'm gonna tell you some more detail than you have to know, don't worry about pulmonary edema, right? Edema is excess interstitial fluid buildup, right? Swollen kind of tissues. So when it happens in the lung, right over here, not only is that interstitial space start filling up with fluid, so what does that do, right? It's increasing that distance, right, in between the two the endothelium and the alveolar space. Excess fluid, longer distance to travel, and pulmonary edema. Also, the edema, if it's bad enough, it starts to fill the alveoli in there, right? And now you got, when the oxygen comes down, right, over here, right, it's got very little distance, right? Very little, all this space is filled up with water, and if it does diffuse too, remember oxygen isn't very diffusible, or soluble rather, it's gonna have a hard time getting to the actual exchange membrane, right? So pulmonary edema. So basically what's happened in pulmonary edema is that, remember this is a capillary bed, you got filtration, right? Pressure coming into it, you got absorption leaving it, right? Normally, the pressure is pretty low in the pulmonary system, right? And then the edema system, the lymphatic system is pretty good at sucking everything up. And so, and again, I'm telling you this, I'm not gonna actually test you on it, but you're a health professional, somebody asks you, hey, I got pulmonary edema, what is it, doc? You're like, I'm a nurse, I'm not a doctor first. And then you say, well, I can tell you that, I'm a smart person. You say, well, there's some kind of problem, maybe your mitral valve wasn't working. What happens when your mitral valve didn't work? Right? Every time you squeezed out, right, instead of going into your systemic blood, right, it was going back into your left atrium, right? What does that have to do with the lungs? There's backup, right? Your right side of your heart is working just as strong, pumping a lot of blood into the lungs, but it's not receiving enough because your left side of your heart isn't pumping hard enough, right? So you get backup in the lungs, and then that whole interstitial fluid, which is, there's an excess filtration basically based on the high blood pressure. And that's what's happening with, when you get things like mitral valve, this is what mitral valve failure, weakened ventricle, left ventricle output, right? The pulmonary pressure could increase like that, right? Because it's backup basically. And so that's pulmonary edema. That's basically what you want to know about pulmonary edema. You're increasing the diffusion distance, right? Slowing gas exchange down. So those could also happen. Right? Here's a slide. This is from back in the day when they're trying to explain what happens during a bad respiratory infection. I forgot whether they were talking about this or something going around. And, but if you watch the slide, right, there's normal oxygen, there's normal blood going through, the oxygen leaving off carbon dioxide. In this condition, over here the blood's coming through, but you got this swollen interface over here, right? The interstitial space is swollen, right? So you don't get this nice oxygen in, carbon dioxide out. Here, you get swollen tissue, not only that, fluid buildup here, oxygen comes in, right? And there's really not where to go, right? So this is something that happens when you have a really bad respiratory infection and everything starts swelling up. The fluid starts accumulating in here, right? And all this is going to affect the diffusion of oxygen into that bloodstream, right? Which is what we want. Right. And then another one, we talked about fibrosis as this restrictive disease, right? Something that was stiffening the lungs, making it hard to breathe. But the other thing is, when you have that fibrosis, you get scar buildup, you get it in between the interstitial space. Right there, collagen instead of elastin makes it more stiffer, but it also, if you get scar tissue in between there, right, what was previously a very short distance to go, over here it becomes this kind of long distance between this like very unpermeable kind of space right here, right? So this is one of those things that also increase the distance, right, which is a big factor in diffusion, right? That was a R4. You increase the distance a little bit, centimeter a little bit, or sorry, it's R squared. It's going to have a large effect on diffusion right there. So anything that affects this distance in between your alveoli and your capillaries are going to be affecting that diffusion difference, right? So just basically pathological changes that are adversely affecting some sort of gas exchange. The last one, we talked about emphysema as a problem with being too compliant, that is too easily stretched. That's not the biggest problem with emphysema. The biggest problem with emphysema is decreased surface area. Okay? So in that case, basically instead of having one over here, right, you got 1, 2, 3, 4, 5, whoops. Right. Where are we? And then over here you got an alveoli sac, right, with all this surface area over here. And now you got one big floppy one over here, right? The elasticity has been lost, but also you're losing a lot of surface area. Right, so instead of that big racquetball court, maybe you got a chalkboard or something like that, right? You've decreased the surface area. Right? So all these are adversely affecting the gas exchange itself, right? And this is just a summary of some of these things, right? All right, so these are all affecting all this gas exchange. All right, so for all that we just talked about, this chart right here, alveolar gas exchange right here, and over here, you got the composition of the inspired air would be the situation when you are, for whatever reason, oxygen was low. Most common thing you encounter there would be actually basically your altitude change, right? But for whatever reason, your composition, the low oxygen content would decrease that pressure gradient. And the other things that would have the gas not coming in is just basic alveolar ventilation, right? And a lot of that what we talked about yesterday, right? And then the other part, once the gas is in there, we have the gas diffusion properties, right? Surface area, what kind of thing might decrease surface area? Emphysema. What kind of things might increase diffuse distance in between your airspace and the blood capillaries, right? You want to think of that interstitial space. It's edema, right? Pulmonary edema would be one. Fibrosis, even though it's not listed in the book, but that would be something else that would increase the distance, right? The barrier thickness, though, would definitely be influenced by fibrosis, right? You basically, that's not the nice, smooth, like layer where oxygen is diffusing right amount there, right? And the amount of fluid, of course, will also be associated with edema of some sort, right? And then the other thing, again, we didn't really talk about this, but you have to have an adequate blood flow going through there for the blood to pick up that oxygen that once it's in there. And so all these will affect alveolar, right? And then, kind of related to this, it's not anything that's gonna be changed or anything like that. This is definitely a constant thing, but it brings us to our next subject is the solubility of a gas, right, in a liquid is also gonna affect it. It's less soluble, right? It's gonna be harder to move through, right, to the next area right there. Some things are more soluble, some things are less soluble. Right? So this is the next kind of topic here. It's a little bit more, I don't know, a little more complicated, a little more confusing, especially this part. Right? If you look over here, you got the partial pressure. I said once you get in the alveoli over here is 100 millimoles per mercury right there. That's the partial pressure. Over here, that partial pressure on the arterial side is going to be something like 40, let's say. So it's an obvious thing. It's going to move from there to there. And then that partial pressure, it's going to move, that alveoli is going to move into this until this blood becomes 100, right? So now we're down to this. However, there's a concentration in the gas part over here, right, that was 5.2 millimoles per liter. That's the amount of oxygen at 100 millimeters per mercury. At 100 millimeters per mercury in a fluid, that is the plasma over there, there is like a lot less right here, 0.15, which is about, I did the calculations on myself, that was about 35 times more concentrated over here than over here. Despite the fact that the pressure, partial pressure was the same. And you don't have to understand why, because I'm not going to tell you, because I don't really know, to be honest. I'm going to be honest with you. I don't know. I looked it up. I looked it up on Google. I asked ChatGPT. I couldn't get a good answer that way. I could spend a lot of time researching it and trying to tell you about it. Just accept it, right? The partial pressure and concentration difference is very different. They don't really apply to each other for some reason. It has to do with the solubility of the gas somehow, but you just have to accept that the concentration gradients is gonna be very different. That is, 100 millimeters of mercury is gonna be exerted by this amount in a fluid, and 100 millimeters of mercury is gonna be exerted by that amount in an air, right? It's just less. There's very little, there's actually very little that's gonna be able to dissolve in there before it creates that, abolishes that concentration gradient. Okay? So that would cause a problem. It would cause a problem because 0.15 millimoles per liter is not anywhere near enough for us to survive, not to meet the body's functions, right? If that's what all we were depending on, dissolved gases in the blood, okay? So this all has to do with the solubility of a particular gas, right? You got, over here, you've got 100 millimeters, 0, and it's gonna move toward that lower concentration gradient, but only a little bit is gonna be dissolved before that pressure is met, okay? Just accept that, for whatever reason. Right? That's what it means. It's not very soluble. It doesn't dissolve well in there. It doesn't want to do it. That's as far as it goes. It goes until it reaches that equilibrium in between here and here. It's just that the concentration gradient is not that much, right? CO2, on the other hand, will dissolve a lot more easier. Right? You see the difference between here and here. That's 35 times. This is less than twice as much. So CO2 is fairly soluble in gas right there. And that's why we could have carbonated drinks and stuff like that. That's also why it fizzes on the top, because it does want to get away from it a little bit and equilibrize. So it's a little more soluble. So if that's not enough, when they say 100 millimeters for mercury, it's a very low concentration. How can we still live? How is it possible? You want to guess? First of all, is it possible? Can we live? Yes, we can live. We're living. So what's going on is the question. Why, how can, with so little oxygen dissolved in the plasma, it's not enough, I'm telling you. Okay, I'm gonna tell you, I knew you'd get thinking anyway, you're just too shy. Basically, every little bit of oxygen that goes in the blood that's dissolved in there, you get one oxygen, it's quickly sucked up it goes into the red blood cell, quickly soaked up, right, by the hemoglobin. Right, the hemoglobin's a pigment. It's the pigment that gives your color of your blood the red color, right? If you were like a bug, instead of hemoglobin, you'd have some kind of other pigment, like green pigment. That's why their blood is like a different, like green and stuff. Basically, the pigments, the hemoglobin in there binds oxygen, and as soon as that 100 millimeters is going over to the 40 milliliters, it's constantly sucked up, right? It's constantly sucked up until all those hemoglobin are filled up, until basically the outside ones, the ones that aren't bound to hemoglobin, are going to be 100 millimeters on the outside of the plasma. So you got a lot of oxygen coming in, but it's all being soaked up by the hemoglobin. Okay? But understands that point, to that far, right? That's where all that oxygen is going. Doesn't dissolve well, it's got to be carried by hemoglobin right there. Right? So dissolved gas is accounting for very little of the gas, the oxygen in your blood. It's all carried in the red blood cells on hemoglobin. Okay? So that brings us into this next sort of topic right here, right? How are we transporting oxygen through blood, through hemoglobin, the properties of the hemoglobin, how it knows when to release in order to pick up oxygen, right? Any questions so far? Not this time? Okay. So again, without hemoglobin, right, it wouldn't be enough. Right? You wouldn't be enough. Most of the oxygen that's diffusing in, right down that concentration, immediately picked up. So there's an immediate low concentration of oxygen in that arterial blood, in the pulmonary arteries right there, because basically the hemoglobin's picking it all up. And so it'll keep on picking up until we have that 100 millimeters of mercury on each side right there. So basically everything that comes in, every little bit of oxygen, almost 98% of the oxygen is picked up by hemoglobin. Okay? So once it's in the hemoglobin, the red blood cells are gonna file through, right? They're gonna file through that capillaries right there, and then be transported throughout the body right there, okay? And so hemoglobin, it's gonna bound, it's gonna form this hemoglobin oxygen structure over here, I'll just call it hemoglobin though. And it's gonna bound to it, but of course we know at some point it's gonna drop it off, right? And so it's a reversible reaction is basically it. Right? And this kind of was something we never really got into so much, but way back when we talked about enzymes a little bit, or maybe about ligands and receptors and stuff like that, things bind to things and then they hop off. They bind to things and they hop off, right? And some things bind tightly, some things bind less tightly. For instance, if you were breathing in a lot of carbon monoxide, right, that binds very tightly. It binds more tightly than hemoglobin, than oxygen, which is why carbon monoxide is deadly, right? It basically displaces the oxygen in there. So things bound at certain degrees, right, of tightness, right, and they're released, right? So basically, if we were breathing in oxygen and we had no hemoglobin, right, that wouldn't be enough to support life. Right? Every little bit, basically, of oxygen that comes in is going to be picked up by the hemoglobin, right there, right? And if there's low levels of oxygen, basically, right, the hemoglobin will pick up that proportionate amount right there, right? It's going to pick it up. Right? If this was 28, right, over here the pressure is going to equalize. Over here it's going to pick up whatever that pressure difference is in over here, right? And the other thing to notice about this is that 98, when it said 98% over there, it's picked up all that oxygen right there. It's basically way more than enough than your body needs right there. So your body actually has excess when you're breathing normally and everything like that. Your body actually has excess oxygen carrying capability, right? That can be called upon when we need it, right? So hemoglobin is transporting oxygen around the blood, right? So, second part over here, just to relate it to the first part, when we talk about oxygen dissolved in the plasma, over there, that's a big difference. We need that pressure differences. One of the reasons we need that pressure is we need a certain amount of oxygen in the blood, and that will lend itself, that will kind of lead to a certain percentage of saturation of the hemoglobin. That is how much oxygen is actually carried on the hemoglobin right there. And how much oxygen was in that initial partial pressure differences is going to be reflected in how much oxygen is carried by the hemoglobin. Right? So the amount of oxygen bound to hemoglobin is going to depend on this plasma oxygen, which was determined by the amount of concentration gradient. Right? And then the amount of actual hemoglobin, this we're not really going to cover so much about the amount of hemoglobin or anything like that, but that's also, these are what's going to depend on the amount of oxygen, right? So here's what we're going to see. All around the alveoli, right? That's where the pressure was highest, and that's where the diffusion rates were highest, so you have a lot of high oxygen levels. Right? So what happens in that case? Right? Oxygen is going to go and bound to hemoglobin. Right, the red blood cells, which are mostly depleted at this point, they're coming from the deoxygenated blood. They're traveling in through those capillaries over here, and then all that oxygen is going to be sucked up. It's going to be sucked up by the hemoglobin right here. So all that oxygen immediately goes into the red blood cell. Oxygen is bound to the hemoglobin. Okay, because it was empty. Now it's full. Right? So what's the next step over here? Right? Once it's bound to that, over here, once it gets to the body tissues over here, oxygen level, the opposite's going to be true, right? Oxygen levels are low because the oxygen body tissues are using it, right? So what happens in that situation, right? The oxygen is going to release, right? Let's go back again. It's a nice graphic, right, to show you the difference here, right? High levels. Right? High levels of oxygen right here, right? In the lungs. Right? And oxygen is bound there. So the hemoglobin knows, okay, there's a lot of excess oxygen, let's pick it up. Right? Travels around the blood. Now we're getting to low oxygen areas, right? Low. And when I say low too, we mean low partial pressures, right? And the hemoglobin says, okay, I wanna release it, there's no use in me, this is the whole purpose of my being, to release this oxygen into these low starved areas. So in other words, your hemoglobin is going to bound a lot of oxygen when oxygen level's high. And then when oxygen level is low, it's gonna release a lot of oxygen. And the more lower it is, the lower the oxygen level is, and other signs that the cells need more oxygen, it's gonna release more oxygen. Remember I told you, there's like 4 times as much oxygen bound as we need, but we can release more if we need to. We making sense so far, that principle, right?
You said this depends on the pressure gradient or the
The
concentration?
pressure gradients of the gas, right? The oxygen surrounding the red blood cell is gonna be a certain pressure. The higher it is, the more oxygen, the more hemoglobin is gonna bind oxygen, okay? So the higher the pressure is, that's indicating a high oxygen content like you see in the alveoli. So the hemoglobin is gonna bind a lot more. Now you get to an area where there's low oxygen levels in the plasma, okay? And the oxygen is gonna say, the hemoglobin is gonna say, okay, obviously there's low oxygen, the tissues need more oxygen. I'm gonna release more oxygen. But it doesn't really just say that, there's a mechanism. Right? That would be teleological thinking. We are a mechanistic type of class. Right? And here's the mechanism. Here's where it gets a little torturous. And I even debated, I was gonna say, I should skip this, but this is actually the most important part about this, the whole blood, this whole pulmonary system, blood carrying right here. Because it's an actual, they use these kind of curves, right, to see what's wrong with people, right? And here's a little bit of the mechanistics. I'm not really gonna ask too much about the details here, but I want you to understand that the hemoglobin, the whole hemoglobin structure, right, it's the oxygen is attracted to this iron subunit over there. This is why we need iron in our diets to carry around. Right? Don't worry about that. But when one oxygen binds one subunit, right, and this would be, obviously, if it's binding a subunit, right, there's low oxygen levels. The hemoglobin, rather, doesn't have so much oxygen. So it binds it, and for whatever reason, it's a shape change, whatever, it's magic. Right? It happens that the other one say, hey, let's bind more oxygen. So the binding of one of them is going to increase the affinity of the other ones. So the signal for binding more oxygen is binding one oxygen in the first place. And so, oh, there's oxygen. Let's open ourselves up to pick up more oxygen is the general idea right there. So when oxygen binds one subunit, the others are showing increased affinity. It's a shape change, whatever, right? However, now you're loaded up. You're loading up and you're going over to a area of low oxygen pressure, which means, hey, this tissue must need oxygen. Let's start releasing. The signal for that is if one of them unloads, then the other ones start unloading more. Again, do you have to understand exactly why? No, right? But that's just what happens. And the bottom line is this, picture, if you can kind of keep this in mind, maybe that'll help. This when plasma levels, that means the partial pressure concentration of oxygen are high over here. That's going to lead to increased binding by hemoglobin, right? And if oxygen, partial pressure, plasma, and stuff dissolved in there, that's the signal. If oxygen are low, decreased, right? That is going to really cause an increase in release of oxygen, right? That's the general rules, basically, for oxygen and how hemoglobin is going to bind to it. The rules for binding and releasing. Just think about that for a second in terms of what the whole purpose of the red blood cells and the hemoglobin are doing. They want to pick up oxygen and carry it around to tissue that needs it. Where does it need to bind? Where there's a lot of oxygen to pick it up in the alveoli. Where does it need to release? When there's low oxygen, because cells are working hard, right? So there's a binding and there's a release. And here's where we get into charts again, dissociation curves, right? The dreaded oxygen dissociation curves, because there's conditions, mostly just determined on pressure, but there's a couple other variables that are actually also affected, right? We're going to just learn some general principles here to try to understand, right? So, here's the curve. Here's the curve right here. Again, excess oxygen right, is going to facilitate more binding, right? So here we have down the bottom, here we have excess binding at like 100%, let's say 80%, even all the way up to here, right? You got something down over here, right? 70%, right? You're pretty much saturated. So if the oxygen levels are 70%, your percent saturation over here is almost 100%. You'll notice the curve kind of goes flat over here, right? So at a certain point over here, you've almost maximized the binding right there. And this is all about the partial pressure over here, right? Does this make sense so far, the curve? We understand the curve here. So I asked you, what is the saturation at 40 millimeters per mercury? What would you say, roughly speaking? What would the saturation be? Just looking at the charts.
70.
Something like that, right? You get about 60%, right? Something like that. Somewhere down over here, right? Something like that, something 75%, okay? Does this make sense so far? You have a high oxygen level, and your oxygen wants to take it in. It's indicated that the cells aren't using the oxygen, there's just a lot of it around. They want, the hemoglobin wants to pick it up. Okay. So this maximum part would be after it's picked up from the alveolus, leaves to the pulmonary veins, back to the heart, it's pumped out into the circuit right there. Your pressure is very high, the saturation is very high. It's going to travel to oxygen-starved tissue, right? And it's going to meet this situation where it's going to deliver that oxygen, right? So it's going to leave, the oxygen saturation level is going to decrease right there, okay? So you're down from 100%, right over here, and then you're moving down to about here. This is the average pressure of oxygen leaving peripheral tissues as it's dropped off a lot of oxygen. And so it's gone down from 100 millimeters or so to 70 millimeters or so. I'm sorry, 40 as far as the pressure goes, right? That's the partial pressure differences, and your saturation has gone from 170. So what does that mean? The hemoglobin coming into a tissue is 100, it leaves at 70% saturation. That's still pretty saturated. So when I say deoxygenated blood, it's not really deoxygenated, is it? It's just mostly, this is normal, sort of not so active tissue. This is just standard average. Okay, that makes sense so far? Think about it. I'll give you a minute. Think about that for a second. The oxygen, the blood leaving there, the hemoglobin, the blood cells leaving there have still about 70% saturated, which means if the tissue is acting, needing a little more, it's got more to give, doesn't it? That's what you were thinking, right? You were about to say that. So from this area, right, over here to where the oxygen saturation was about 20, that's a very steep curve, right? It's going up very high. There's a very fast dissociation or binding, however you want to think of it right there. The pressure of the oxygen when it's very low, right, that saturation is going to be very low, which means if the tissue was working really hard, it was a skeletal muscle, if it's working really hard, that means basically that is going to have used up all the oxygen you had very low, right? So basically that's why the saturation rate is also very low, because the hemoglobin was releasing the oxygen all at this point, okay? And that's why it's very low. So you have this much, you have to go from 70 to here, you had all that to spare, right, in hard working tissue. Okay? So that steep curve right there, look at it, this would be like the pressure of active muscles over here. Right? So you have this much to spare, right? So the fact that when you're not working so hard, but your hemoglobin is very ready, very easy to give up a lot more oxygen in response to that hard-working muscle, right? Low oxygen levels. So this is the hemoglobin, this is the oxygen saturation, the binding curve, the saturation curve, the dissociation curve. It's called a couple things, right? That's the binding curve. But the bottom line, as far as principle goes, right? When there's high oxygen plasma levels, the binding is going to be high, right? And that's indicated right up here. And high oxygen levels, high down here, right? And then whereas low plasma oxygen levels over here, are gonna be met, the low pressure rather is gonna be met with low saturation, not met with, but responded by leaving off a lot of oxygen, which will leave the hemoglobin less saturated. Okay? So, you got the steep phase, right, over here, and you got the plateau phase over here. So, if I asked you, what tissues do you think you'd see? To say something over here, and from here, what capillaries are we talking about here? What? Muscular would be like a hard-working muscular stuff would be at the low end, right? And then just basically over here, this is, I mean, in short, it's body tissues, right? Depending on how hard you're working, you'd go from, this is very hard working. Over here, this is lazy. Over here, and this is, where are we here? In the plateau phase. Where is most, where would you find an area with a lot of oxygen? Pulmonary, right? In your alveolar, around your alveolar space, right? Around your alveoli capillaries, right? That's where the oxygen is diffusing in, right? These days, I took a whole semester off and learned how to write, but. All right, that's the general idea. Does that kind of make sense? That's the oxygen dissociation here. Understanding? Okay. So, once again, we talked a little bit about the shape change, about levels of oxygen, right? However, there are other things that are gonna affect that dissociation curve, the binding curve right here. And those things are pH, right? Levels of acidity in the blood is gonna affect how much oxygen is released or bound. The temperature of the tissue is going to affect how much oxygen is bound and how much is released. And the partial pressures of carbon dioxide. Right? All these ones up here, decreased pH, that is a higher acidity, more hydrogen ions, are going to reflect increased metabolism. Temperature is going to reflect increased metabolism, right? Because as you're working, you're letting off heat. And carbon dioxide production is also going to represent increased metabolism. In all those cases, you want more or less oxygen? More. And then, does the hemoglobin want to release more or take more in? Release more, right? It wants to release more. So the oxygen dissociation curve, that curve we saw, is going to be shifted a little bit. It's going to shift it to the right a little bit, right? Because it's going to represent decreased affinity, right? Because there's these mechanisms here that are going to decrease the affinity for oxygen, so more oxygen will be released. Same thing, the lazy cells are non-working cells so much, right? That would be an increase in pH, a lower body temperatures, and less CO2 produced are all going to represent basically lower activity in a cell right there. So here's these dreaded dissociation curves. Here is the effect of carbon dioxide. So what's the carbon dioxide do? Basically, it's showing that there's a lot of activity going on and we need to release more oxygen. So that whole curve right here, you're going from pressure of CO2 to normal, and the red right here would be the normal one. Right? And if there's a lot more CO2, that is the partial pressure is increased, we're going to shift that to the right. Right? So if you look at, let's say at 40, the pressure is 40 over here, right? You are 70% saturated, right? Whereas at 80, right, you go down to about 50%, which means you're letting off more. Does everyone understand these kind of charts right there? So, right, over here at 40, this is like the standard CO2 kind of level that you're releasing right there, right? At 40, over here, you get to the red. This is the normal POC, this is like the normal one right here, right? At this pressure right here. And you're releasing, you're saturated around 70%. Whereas if you were at 80 millimeters, the CO2 was a lot higher right here. Now you're going to shift it over here. So that same 40 the oxygen status is gonna be around 50%, right? So you've gone from 70 to 50%, right, with excess carbon dioxide. So you're releasing, that is, the hemoglobin is releasing a lot more oxygen, it's less saturated. In that situation, when there's more, higher CO2. And the opposite would be true for the other end. Okay, that makes sense? Basically, you just shift it. You understand the principle, if nothing else, okay? Will I put one of these on the test? No, I'm not going to. I want you to understand the questions though. Higher levels of cell activity are gonna produce more carbon dioxide. Okay? Higher levels of carbon dioxide are gonna cause a greater release of oxygen. That's the general principle you wanna understand right there. That's CO2. What else is another sign of? It's called temperature. I'm not gonna go over, but the temperature is gonna show a higher temperature. You're gonna basically increase, that's gonna show increased activity, right? You're increasing heat release during that whole respiration process. That's gonna also shift the curve the same way, right? The lower pH, that is higher acidity content, more hydrogen ions floating around, that's called the lower pH. And that would be 7.2 as opposed to the 7.4 right there. One of the things that might increase hydrogen content, one of the things, there's also another thing, but one of the things, if you're going to anaerobic respiration, right, you're going to lactic acid buildup, that's gonna cause more hydrogen release, blood pH is gonna drop. That lower pH is causing a more release from oxygen because it's indicative of higher activity, right? That makes sense. You got the general principle? Sure do. You're making it so easy. Good, thanks. I tried, but. So everything here, right, is about oxygen content, right? How we get oxygen in, whether we get it in, how much oxygen is part of there, whether you're in high altitude conditions, right? And these kind of things that we talked about yesterday, the diffusion properties, right? And all the things that might affect that. And then here, we have this percent saturation, right? Oxygen bound to the hemoglobin, right? Which is gonna depend on the concentration over here, but also these other factors right here. We're not gonna talk about these other things right here that are kind of grayed out. Okay? All right. That's just oxygen. Let's see how far we get here. I'm gonna do this next time. There's also carbon dioxide is more diffusible in blood. It can go from your hard-working cells over here being produced as a waste product. It's going to travel through from the cells, go through the interstitial space right there into the bloodstream, and it's going to be soluble to some extent, but the other way it's going to be carried is in red blood cells, and there's a couple different things that are going to happen in here, right? So this is what we're going to be talking about here. Here, how we carry carbon dioxide around, how it changes basically to other products right there, or down to hemoglobin and other factors right here. I'm gonna walk down the steps. Right, so over here, right, the cells over here, we're making up, during cellular respiration, we're creating a lot of carbon dioxide, right, build up over here. And then so carbon dioxide is gonna diffuse out of those cells, right, and into the systemic capillaries, right, that we're flowing through those tissues right there. Where's it going to flow in? Remember the venous end, the pressure differences, osmotic pressure, all that fluid is being drawn in, CO2 is being drawn in with it. Right? And also due to partial pressure differences, right? And then the second point over here, only about a little bit of it, it's more soluble than oxygen, but not that soluble. Only about 7% is actually traveling as CO2 through the plasma, right here. About a fourth of it, when it enters the red blood cell over here, is going to be going into hemoglobin. Remember, we just dropped off a lot of oxygen. We have some room. Now the carbon dioxide can actually bind to hemoglobin in those empty spaces and hitch a ride back there as this molecule hemoglobin carbon dioxide thing, right? That's about a quarter of it. You don't have to know the name of that. It's just bound to the hemoglobin right there. Other parts of it, right, that CO2 is going to combine with water under the guidance of carbonic anhydrase, an enzyme. That CA right there is an enzyme. And it's going to convert carbon dioxide to this bicarbonate acid, right? Carbonic acid, H2CO3. H2CO3. It's a carbonic acid. What do carbonic acids do? What do they release? Typically, if it's an acid, it would release that hydrogen. Right? So it's going to turn into an anion, bicarbonate ion over there, right? So that carbonic acid is going to turn into that HCO3. Okay? So this is actually an important part when we talk about acid-base stuff. We'll leave that off right now, but this levels of bicarbonate ion is a big buffer system. The hydrogen, that spare hydrogen is picked up by hemoglobin again. It's also picked up by hemoglobin to make this hemoglobin hydrogen kind of substrate, right? That's going to also be carried through there, right? And then the next phase is the bicarbonate, the bicarb ion. Ion over here is going to leave the red blood cell and it floats through the plasma, and also it's going to mix in with the extracellular fluid, the interstitial fluid. Again, this is your main buffer system, right, maintaining pH over there, this bicarbonate ion as it floats through. So this is an important part, right, when we talk about that. Okay. I didn't mention this, and I won't test on it or anything. I forget if I put it in learning objectives, but the way it's transported out is anion for anion chloride shift. Don't worry about it, actually, never mind. In any case, right, that dissolve, basically, at this point, your bicarbonate ion is floating through the bloodstream until it gets to the lungs. Over here, there's some carbon dioxide over here that's going to go in there. But the other stuff, right, that bicarb ion is going to be transported back into the red blood cells, right? You need a cell for this activity to happen, right? Because basically what's going to happen is that bicarbonate is going to meet up with the enzyme again, right? And that hydrogen is going to be supplied by that hemoglobin there to turn this carbonic anhydride, the carbonic acid back into CO2, which now leaves the red blood cell and dissolves back in here based on its concentration gradient. Okay? We can go over this again tomorrow if it or in lab or anything, if it doesn't make total sense, but that's what's happening with carbon dioxide transport, right? So the big medium players are this bicarb acid, right, and HCO3. It's floating around the plasma, right, and that extra hydrogen is picked up by the hemoglobin, right, ready to give it back when we need to turn this back into carbon dioxide so it can diffuse out into the lungs. Right, so that's basically everything that's happened, right? We have that pressure differences in the alveolar bloodstream, and we're transported by hemoglobin over there, all based on concentration gradients, hemoglobin saturation, all that, right? Bring it over to the cells, carbon dioxide produced, and we transport it back through the systems we just talked about there. And there's one last thing. And this goes back to all the reflex pathways and everything that we talked about, and I'm not going to go into so much detail here. This should be all pretty familiar at this point. There are these levels of carbon dioxide or oxygen and pH that are detected. Right? That would be the variable, that would be the change, the stimulus, right? High carbon dioxide, low oxygen, low pH, or excess hydrogen ions are going to be picked up by receptors of some sort. You don't have to know the names of the receptors or anything like that. They just pick them up. That information is going to be brought into your lizard brain over there, your brainstem, and your brainstem is going to say, okay, we need more oxygen, we need less CO2, and how do you do that? You make your skeletal muscles work harder, you breathe harder or heavier. Right? So all that we do in ponds are basically working on your breathing muscles. All you want to remember is like your diaphragm. I'm not going to get into details on particulars. Right? All right, so this is basically the grayed out stuff. Means I'm not going to ask, but I just understand the basic pathway, and this is something we've kind of covered out the whole way. And the other part of it, the actual brainstem part, is fairly complicated, but I'm not going to ask any details other than the brainstem is controlling these. That's the control centers that are controlling your normal breathing patterns. Right? Your in and out, just your normal, unconscious, tidal volume breathing stuff. right? Those are your pons and your medulla, but it's just the brainstem, that's fine, right? Somewhere in your lizard brain over here. And they're also gonna get monitor themselves or be sent messages from chemoreceptors, right? And then they're gonna respond if it's high CO2 or low oxygen, right? They're gonna respond by breathing heavier and more, right? Somehow increasing your ventilation. Or vice versa, if it was too low. Is there some kind of sensory input? And some kind of things that are monitoring the environment? And then the output is gonna be to your breathing muscles, right? Just think your diaphragm is the easiest thing to think of, right? So this is controlling your normal rate. This stuff, this is your brainstem, even though this is skeletal muscles, it's the somatic pathway, it's stuff you can override it. Right? This is all done unconsciously for you by these brainstem centers, okay? What happens if those brainstem centers die? What happens if they got destroyed? Would you die?
No.
Why?
Carotid body cells.
They're not working. These are your unconscious breathing things. These are the ones that do it for you when you're not thinking. If they stop, you'll stop breathing. What will you do then? Well, you'll use a machine. What if you don't have a machine? What if you're on a desert island? You can consciously breathe. These are skeletal muscles. You can consciously breathe, right? So you don't need those, right? Until when?
You go to sleep.
You go to sleep. What happens when you go to sleep?
You can't.
No, you can't consciously breathe, but do you just die? Or do you wake up?
You wake up.
Right? As I say, I'm snoring, my wife puts a pillow over my head, I get low oxygen, I wake up, right? And that's what would happen if those died. This was an actual disease that happened back in the 1600s. And those people, they didn't die of lack of oxygen because they could breathe, but they died of lack of sleep because they could never sleep, they had to wake up. So even though it's kind of like I didn't really get into the details about inspiration and respiration stuff, it's an interesting part of the brain right there. It controls your natural breathing, right? And will respond. And again, the details of this should also be familiar. Low oxygen pressure sensed by these receptors. We don't have to know it's a glomerular cell or anything like that, right? What we want to know is it responds to low oxygen pressure by a closing of this channel right here. Okay, if I tell you there's a channel closed and the cell depolarizes, what kind of channel do you think that is? It depolarizes when it's closed. That is, it used to be flowing out, and now you stopped it. What kind of, what? No, you stopped it with a mechanical gauge, a low pressure of oxygen, whatever, however, it stopped the flow of ions that was leaving. Now it's not leaving, and now the cell is depolarizing, it's getting more positive. What would make a close, what channel would close to make this more positive?
Sodium.
Potassium. So this is a potassium channel. Okay, this is all stuff that, this is the same kind of themes we've been seeing right here. Right? You close the potassium channel, the cell gets depolarized, more positive, bring it to threshold. When it gets to threshold, what kind of channel here you think might open? Calcium channel, voltage gated calcium channel. This is the same kind of thing. This is the same thing. This is all the same pattern. What kind of thing flows in the voltage gated calcium channel? Calcium. What does calcium do? It causes exocytosis, basically. So all this is repetitive kind of themes that we saw. That's how the oxygen centers do it. We don't know exactly how, but they close that potassium channel. And second, and similar, well, we won't get into the details here, but you have high CO2 levels. This is sensing the cerebral spinal fluid of your brain. And here, if there's too much activity, not enough ventilation, not enough oxygen, not enough flow going through, for whatever reason, that's going to be picked up by central chemoreceptors. Central meaning just it's in your central nervous system, cerebral spinal fluid. That is going to be sent to those brainstem centers to increase ventilation. And the same thing out here, just what we talked about, right? Just sensing low oxygen, high CO2 is going to make us breathe heavier, right? All right. Any questions on any of that? All right. So that's it. And we'll tomorrow. I'll put up some slides tomorrow with the kidney stuff. It's very kind of really big, basic overview stuff. A little bit about the anatomy, but I'll send the figures to kind of study.